Okay, welcome. So I'd like to take you through some aspects of statistical testing of electrophysiological data. So this is a brief outline. So I will start with an attempt to try the question why we need statistics in neuroscience, and that will involve aspects such as the difference between inferential statistics and data analysis. So I will mention the details of a fairly unknown statistical test. It's called the interocular traumatic test, and I will explain why it is useful to understand inferential statistics. I will briefly say something about the general idea behind inferential statistics, and the general idea is, in a nutshell, that is principled decision making under uncertainty. And I will then discuss two different approaches to inferential statistics. And the first one, most of you will know, so-called Neyman-Pearson approach. It's the approach that most of you had in introductory statistics courses at the bachelor level. And then I will go into the permutation-based approach, which will be novel to some of you, but at the same time has some remarkable similarities to the Neyman-Pearson approach, but also a few crucial differences, and these crucial differences turn out to be very useful for neuroscience applications. And finally, I will wrap up. Okay, first question, why do we need statistics in neuroscience? So there are actually two ways in which statistics helps us. First, it helps us in making decisions under uncertainty. And the corresponding branch of statistics that helps us with this question, it's called inferential statistics. And you all know it via its test statistic, like T statistics, F statistics, chi-square statistics. They're all part of this branch of inferential statistics. They're about decision making. Now there is another branch about which I will not talk, but which most of you also know about. It's so-called data analysis. And that part of statistics is used to reveal patterns in the data which you cannot identify by eyeballing. So very often we have high-dimensional data, and just by looking at these data or by summary statistics of these data, we cannot see revealing patterns in them. And therefore, statisticians have come up with tools like factor analysis, principal component analysis, Fourier analysis, that all help us to identify revealing patterns in the data. Importantly, that branch of statistics doesn't involve any p-values at all. But nevertheless, it's very useful. Of course, there are also mixtures of the two. Data analysis with p-values attached to them. So today I will only focus on inferential statistics. So why do we need statistics in neuroscience? Now in 1950 there was a famous statistician, Bergson, and in a challenging paper he introduced the idea of the interocular traumatic test. And this test works as follows. When you look at the data, the conclusion hits you right between the eyes. And this expresses very well why we need statistics in neuroscience. We need it because this test very often fails, because there is uncertainty in the data pattern. Now there are cases, not so frequent, where actually this interocular traumatic test would work. And let me give you an example. Say you have a sample of 20 participants, and all of these 20 participants show exactly the same difference between two conditions, A and B, and the same difference means the same difference across space, the same channels or the same voxels in source space, the same frequency band, say all between 12 and 14 hertz, and the same time interval relative to some stimulus, say all between 300 and 400 milliseconds. In that case, there is almost no uncertainty in your data pattern. And that's when you say the conclusion hits you right between the eyes. Now, as said, the interocular traumatic test very often fails because either the observer is uncertain about the conclusion that can be drawn, so you as as a scientist looking at your data for the first time, you don't know how to make sense out of it, whether there is a real pattern or a real difference between the two conditions or not. Or, that's also very likely, different observers looking at the same data pattern, they disagree with respect to the conclusion. And that very often happens between you and the reviewers, or between you and imaginary reviewers. Because you look at your data and you think, I think this is in the data, but will some other guy, in particular the reviewer, will he also conclude the same thing from that pattern of data? And then you want to settle the issue, either in interaction with the reviewer or beforehand. So you do it with your imaginary reviewer. And statistics is useful for that. So why does the intraocular traumatic test so often fail? Actually, I briefly mentioned already, it has to do with uncertainty. And there are actually basically two types of uncertainty. First of all, there is the uncertainty that is captured under the label signal-to-noise ratio. And every one of you who has already collected neurobiological data, be it fMRI or electrophysiological measures, you will find out that the SNR is typically very small, especially at the single trial level. It's definitely not the case that neither fMRI or electrophysiology is a window on the brain in the sense that a layperson would understand this. Just looking at the data and then observing revealing patterns in the ongoing data. That's not how it goes. SNR is just not sufficient for that. Second, in neuroscience, and that's very different from behavioral science, we work with high-dimensional data structures. And these high-dimensional data structures, they are compared between conditions. And because they're so high-dimensional, you cannot do this on the basis of visual inspection alone. So compare this with a pure behavioral experiment. Typically, every trial gives you two numbers. Either you press the left button or the right button, and you have a reaction time. So you have two numbers for every trial. Now, if you take a subject and put him in the MEG scanner downstairs, we have 275 channel system, and we typically record at, say, a sampling rate of 1,000 hertz. So every second gives you 275,000 numbers. And compare it with two numbers. And then also we have a lot of scientists, especially here in the Donders, they have an interest in frequency, and they create an additional dimension. They create a frequency dimension. You get a three-dimensional structure you get. Channels by frequencies by time. So that becomes huge. So in EEG and MEG, if you compare two experimental conditions, with spatiotemporal data, you have one comparison for every sensor time pair, and if you have a frequency axis squeezed in between, you have triplets. And you have tens or sometimes 100,000 of these triplets. The same problem holds for fMRI, of course, but there only the spatial dimension creates the high dimensionality, but there also you have much more voxels than you have channels. Okay, next question. Do we have something like statistics for neuroscience? And the brief answer is no. I think the general principles of statistical decision making, the ones that we use for analyzing behavioral data, we also use the same principles in the analysis of neurobiological data. However, neuroscience has its own statistical problems. And because it has these problems, it requires specialized methods. And most of these problems, they are due to the fact that we deal with very high dimensional data. And that brings us to the multiple comparison problem. So we typically, in every experimental comparison between two conditions, we have tens to hundreds of thousands of comparisons. And each of them you can make them either using a t-test or an f-test, depending on the number of levels of your independent variable. And the total number of test statistics that you would evaluate at the level of these sensor time pairs or sensor frequency time triplets, each of them produces one p-value. If you do it using the standard statistical approach. And I probably don't have to explain that this, if you do this naively, this results in a drastic increase in the false alarm rate. What is good, very good to keep in mind, as a way to not overvalue inferential statistics, you should keep in mind is that it is principled decision making. At the end, it's about making decisions, and you do this in a principled way. So you choose a particular principle that allows you to deal with the inherent uncertainty in your data. So the essential points are that this inferential statistics is based on rational principles, decision making based on rational principles. And very importantly, there is not only a single rational principle, there are more rational principles. There are not very many, because it's not so easy to come up with principled decision making. So you have to think about this carefully, and for that we have our colleagues, the mathematical statisticians. They look for principled ways of dealing with the uncertainty in our data. But there is more than one, and I will give you a list in the following. Crucially, you can arrive at different conclusions depending on the principle on which your decision is based. And in that sense, you cannot say that statistics is about the truth, or that statistic reveals you the truth. Statistics is not about revealing the truth. Statistics is about correctly applying a particular principled way of dealing with the uncertainty in your data. Now let you give you a list of the 4 most common ways of dealing with uncertainty in your data. The Neyman-Pearson approach, which I will go into in some detail, and maybe you don't know it under this name, but these are the concepts that you are familiar with. It's like the null hypothesis, the alternative hypothesis, type 1, type 2 error, and so on. There is false discovery rate control. It's very popular in neuroscience. I will not say anything about it. I will treat the permutation-based approach, which may be new to some of you. And there is the nowadays extremely popular Bayesian approach. All of them are in principle sound, but they might lead to different conclusions. In particular, the Bayesian approach, some of you who are familiar with the ingredients of this approach, and you know that there is a role of the prior distribution for the conclusion that you arrive at. By giving the prior distribution a very strong weight in your inference, in principle you can arrive at any conclusion. Which is not wise, of course, because the prior should only reflect genuine prior knowledge. But there is an aspect in the Bayesian approach that, for some people, is being conceived as subjective. Okay, so how will I go about this? So for each of the 2 decision-making principles that I will deal with, Neyman-Pearson and permutation, I will illustrate the statistical testing procedure, actually the operational procedure, and I will do this by means of a very simple example. So the difference between 2 means and no neurobiological data at all, just a simple reaction time experiment and 2 experimental conditions. I will explain the rationale behind the procedure. Then I will go to neurobiological data and show how the multiple comparison problem is solved under that principle, and I will then evaluate the solution. So this is how it goes. In the Neyman-Pearson approach, you always start from a so-called null hypothesis. And this null hypothesis always pertains to unknown population parameters. And typically the null hypothesis is about expected values or population means. You also have null hypotheses about variances, correlation coefficients, but the story is the same. So here we focus on expected values, and you have an interest in whether the expected values in 2 populations, typically 2 experimental conditions, A and B, whether they are equal or not. So you formulate your null hypothesis, and then you take some test statistic. And I'm not going to say a lot about this at the moment, how you have to choose your test statistic, but there are ways to select the test statistic, and the most familiar one is the two-sample t-statistic. That's the one that you use if you want to evaluate a null hypothesis of equal means in two conditions, two populations. And the last point, and that's the one where you have to think a little bit about it, because it's also a bit longer sentence. What you should do is you should find the critical value for your chosen test statistic such that under the null hypothesis, the one that you formulate here, the probability of exceeding this critical value is controlled. That is the principle according to which the Neyman-Pearson approach makes database decisions. So how it deals with the uncertainty in the data. It starts from a null hypothesis. It looks for a certain test statistic. For that test statistic, it knows the probability distribution under the null hypothesis, and in the decision-making procedure, one can make use of that known probability distribution of that test statistic under the null hypothesis. And from that probability distribution, which is called the sampling distribution under the null hypothesis, from that probability distribution we can arrive at a critical value, and that critical value is being defined by some critical p-value, typically 0.05, under that sampling distribution. And if you have a t-statistic that exceeds this critical value, then you say that this null hypothesis is too unlikely given the observed data, and you reject it. Okay, so that's the procedure and a little bit of the rationale behind it. There are some constraints to that approach, and these constraints will turn out to be very important when you go to neurobiological data. First of all, the probability distribution of the test statistic under the null hypothesis has to be known. Yeah? So you must, at some point when you pick a test statistic, you must be able to prove what is the probability distribution of that test statistic under that null hypothesis. And that turns out, in general, a very, very difficult problem, which is not something for neuroscientists to solve, it's something for mathematical statisticians to solve. And mathematical statisticians, they have built the so-called normal theory, or the normal distribution-based theory. They have shown that for a whole family of test statistics, of which a t-statistic is the most important one, it is possible to derive the probability distribution under the null hypothesis, but you must make some auxiliary assumptions. First of all, you must assume normality of the data. You must assume that the variance of these data in the experimental conditions being compared, that this variance is equal, and it assumes independence of the observations. Later, when we discuss the permutation-based approach, we will drop those two assumptions, but we will keep independence. So all the statistical procedures I know of, all of them, I say 95 of what I know of assumes independence. And we will also do it here. Now, a second constraint, which is definitely as important and also very crucial for neuroscience, is that the test statistic that you choose should not be just any test statistic. You want a test statistic that is sensitive. You want a test statistic that has a very high probability of rejecting the null hypothesis when it is in fact false. Yeah, because that's what makes us happy. We want to reject null hypotheses, and for that we want to have a test statistic that is really sensitive to the pattern in the data that we consider to be informative and that we hope to elicit using our clever experimental manipulations. So, expressed in the language of statistics, we say that under the alternative hypothesis, the probability of exceeding the critical value must be large. We also say that the test must be powerful or must be sensitive. Yeah. It must have a small type 2 error, so a high sensitivity. Yeah. For neuroscientific data, that turns out to be an important challenge. I will return to that. So what I have said until now, I'm going to try to present this graphically, and I hope that this will also make the concepts behind the Neyman-Pearson approach a bit more vivid. And it requires some notation. It's not so much, but please, I have only 2 or 3 slides of this type. Try to follow me in understanding the symbols. There aren't so many. Yeah. So I'm going to start at the lower right. That's where the variables are being defined. And I have 2 types of variables. I have so-called random variables, and I have realizations. So whenever we do statistics, we consider our data as being generated by some stochastic process. Yeah. And that's being depicted by this capital D. Yeah. The capital D, it denotes the fact that if we would replicate our experiment under identical conditions, we might observe a different value. And the exact value that you record is the value small d. And this small d corresponds to a random variable, capital D. That's the difference between big and small d. So there is some randomness when we generate a particular number. If we observe a particular reaction time in a particular trial, and we do not consider this to be a deterministic quantity. We assume that reaction time could have been different if we would have repeated the experiment under identical conditions. So that's the difference between big D and small d. Now you see there is a big vector here, and this big vector, it just denotes all the data in my experiment, which involves 2 experimental conditions, capital A and capital B, condition A and condition B. And each of the 2 conditions has small n observations. So I have small n observations in condition A and small n in condition B. And to make this concrete, just consider a reaction time experiment involving a single subject who has small n trials in one condition and small n trials in another condition. So this is now we're going to do a t-test on the data of one subject. So later I will also show you how to use the same principle if you want to do the typical analysis over subjects. And then you calculate average reaction times within every subject. But for explaining the principle behind Neyman-Pearson theory, doesn't matter whether you look at the data of one subject and then the replications are the trials, or whether you look at the data of multiple subjects and then the subjects are the replications. So we look now at the data of one subject. Now this one subject, it has generated numbers, 2 times n numbers in condition A and n numbers in condition B. So this is just the vector of numbers that we have in the MATLAB in the MATLAB workspace, and we can now run the MATLAB function t-test, and that will give us a p-value. And the rationale behind this p-value calculation, it is being depicted here. What is being shown here in this rectangle, that's the null hypothesis that we want to test. And the null hypothesis is the following. It says that this vector valued random variable d, with n numbers from condition A and n from condition B, that this vector valued random number is drawn or involves or is characterized by expected values mu A and mu B, which are equal. So I have here n numbers or n random variables, condition A, and here in condition B, each of them has an expected value. And in condition A, they all have the same expected value mu A, and here they have the same expected value mu B. And what we want to test now is whether these expected values are equal. And then we have some auxiliary assumptions like equal variance in the 2 conditions, and we have normality. So that's what we want to test. Now what is the logic behind the test that we perform? The logic is that we calculate a test statistic. And the test statistic is here being denoted by S. Now, you see there are some of these symbols, they involve gray, and I'm going to explain them in a minute. I'm going to start with the observed data. The non-gray, small d, those are the numbers that we have actually collected. I calculate the test statistic, which is going to be my two-sample t-test, and then I'm going to evaluate that test statistic as under the reference distribution, which is going to be my t-distribution with 2 times n minus 2 degrees of freedom. And I evaluate whether that observed test statistic is somewhere in the tail of that probability distribution. The question now is, where does that probability distribution come from? And that is being explained by these gray numbers that you see here. These gray numbers, they are D1 hat, D2 hat, they are all non-observed. They only exist in theory. But these gray numbers D, these are the numbers that would have been observed if we would have drawn data from the null hypothesis. In practice, we do not know whether the null hypothesis is true for the variable D, which govern our data. But the game that we play is we think or assume temporarily that the null hypothesis is true. Then if the null hypothesis is true, we can collect imaginary data, which are these gray symbols. For each of these gray symbols, we have a test statistic. And if we would then have an infinite number of these test statistics, make a histogram of them, then we will get our reference distribution, our t-distribution with 2n minus 2 degrees of freedom. Yeah. So that's the idea. So the gray numbers are the ones that generate your reference distribution, and the black number, evaluated at its test statistic, it's the value that you're going to use to find evidence against this null hypothesis. If that test statistic is far in the tail of the distribution that you get under the null hypothesis, you find it unlikely the null hypothesis to hold. Okay, so that's the idea behind it, and now let's see what we have to do if we want to apply this, not to scalar observations, reaction times, but we want to apply this to a data set which has 100,000 of samples, like an MEG data set. Now, how you go about that? What you do now is you formulate your null hypothesis in terms of unknown population parameters at all elements of the multivariate random variable D. So this random variable D now is not just a scalar, one number per trial, but it is tens or hundreds of thousands of numbers per trial. But still, it is some random variable that has some expected value. But that's a huge array. In electrophys, it pertains to channel frequency time triplets, and for fMRI, it pertains to voxels. And the second step, it's also the same as in the univariate case, but with different data structures. You calculate some test statistic that depends on the data at all the elements jointly. Yeah? And what has been very popular in fMRI is to use the so-called maximum t statistic. Yeah? So you have, in fMRI, you have few 10,000s of voxels. Yeah? And for each of these voxels, you calculate a voxel-specific t statistic, and then you aggregate over the voxels by taking the maximum t statistic. Yeah. And there's also other types of statistics that are based on thresholding and calculating the size of the largest cluster. So there are different types of ways to aggregate the voxel-specific t statistics. The third step, once you have this aggregate statistic, you find the critical value for this test statistic such that under the null hypothesis, the probability of exceeding the critical value is controlled. That's just the same as in the usual univariate case. The main thing is that you have this very unfamiliar test statistic in between. It's not a t statistic, but it's a maximum of a very large number of t statistics, or some other way of combining these t statistics. Now, let's evaluate this. First, with respect to the constraints auxiliary constraints that you have to assume, that turns out to be quite challenging. It turns out that if you want to calculate the sampling distribution of that maximum t statistic or some other aggregate statistic, you have to make auxiliary assumptions which are more strict than what you have in the univariate case. And some of you may have heard about the Gaussian random field, and that is the main auxiliary assumption. So if you assume that a Gaussian random field holds for your data, then you are safe to apply, or then you can apply reference distribution for instance, the maximum t statistic. A second point, just as important or maybe even more important, the test statistic for which you know the distribution under Gaussian random field, that distribution may have a very low power. Yeah. The question is, what is this power? How can we calculate it? This is a very difficult question, but for the rest of the talk, it's very important to keep in mind that it's not only important to have this aggregate statistic such that you know its reference distribution under the null hypothesis. You also want to have a test statistic that is sensitive for the type of pattern that you are likely to encounter in your data, or that you hope to encounter in your data. Okay. Now, I have to make a very brief sidestep now before going to permutation-based inference. Now, that's about the difference between, at the one hand, between unit of observation designs and within unit of observation designs. Because in practice, we often analyze data of individual subjects, but when we report in a journal article, we report about the results obtained of a large number of subjects. And for that, we have to make a distinction between these two types of design. Whenever I say unit of observation, for your own understanding, you may also replace this by subject or trial. Either a trial is a unit of observation or a subject is one. Now, what is the crucial distinction between those two types of designs? Okay, that comes in the second point. First point to be made is that in practice we work either with collections of trials, that's what you have in a single subject study, or you work with collections of subjects, and that's what you have in a multi-subject study. So trials and subjects are jointly denoted as units of observation. Now there are two types of experimental designs, the so-called between unit of observation design and the within unit of observation design. And in a between unit of observation design, every unit of observation is observed in only a single experimental condition. Whereas in a within unit of observation design, every unit of observation is observed in all experimental conditions. So a single subject study with multiple trials, it's always between unit of observations, because a given trial is only observed in one experimental condition. This does not have to be the case when the unit of observation is a subject. Typically, in the experiments that we run here, every subject is being observed in multiple experimental conditions. So we have tasks where attention is to the left of the visual field, the right of the visual field. We have tasks where we give a cue or no cue. We have high working memory load, low working memory load, with motor preparation or without motor preparation, and so on. And typically the experiment that we run is such that in one experimental session, trials are being collected of the multiple experimental conditions. At the end of the experiment, you calculate the average across the trials within every condition, and so for every subject, you have at least two numbers, one for condition A, one for condition B. You also have between subjects designs, and that's what you have if you compare different groups, like if you compare young and old, if you compare trained subjects with novices and so on. In that case, every subject only provides data of one condition. And that is, from a statistical point of view, the same as when you would be analyzing a single subject study. Because in a single subject study you have trials which are also being collected in different experimental conditions. And that's why this two-sample t-test is both used to analyze single subject data. It's also used to analyze multiple subject data where each subject comes from a different group. But that's statistically just the same framework. So having that in mind, I should tell you something now about the within unit of observation design. And that's the type of design that you deal with when you have multiple subjects. And in practice, you use the paired samples t-statistic for it. Or it's also called the dependent samples t-statistic. And actually the story is just the same as with the between unit of observation design. The only thing that is different is that the variables that you put in, they have a little bit of a different structure. But the way you think about it is just the same. There are actually no new concepts here except for the definition of the input. And now what you see here is that as compared to the between unit of observation design, now the data come in pairs. Now you see every row here is one subject. And I have small n subjects. And every subject has been observed in condition A and in condition B. The data come in pairs. That's the crucial difference. And because the data come in pairs, you analyze them in a way that respects the fact that the data come in pairs. And that's also reflected in the auxiliary assumption that you make. Now you assume the so-called bivariate normality as your auxiliary assumption. And under that bivariate normality, your dependent sample t-statistic has a t-distribution with n-1 degrees of freedom. Okay, I'm now going to introduce the permutation-based approach, starting from the Neyman-Pearson approach. I'm going to focus on the differences. And there are just a few crucial differences, but for applications it makes a lot of difference. So how does it work? I take the three steps that I also used for the Neyman-Pearson approach. I start with formulating a null hypothesis. And now the null hypothesis, crucially, does not pertain to expected values, but the null hypothesis pertains to probability distributions of the observations. The null hypothesis pertains to these capital D variables. This capital D is the random variable. It has a probability distribution. And what we're now saying in our null hypothesis, or claiming in our null hypothesis, does not pertain only to the expected value of D. No, it pertains to the probability distribution of D as a whole. So what we're saying now is the probability distribution of the observations in the different experimental conditions, they're identical. So that now becomes our null hypothesis. So we have two experimental conditions, each governed by one probability distribution, and the null hypothesis you want to test is that they're identical, these probability distributions. Now, second step, we take some test statistic, and now there is no constraint about whatever test statistic you choose. It turns out that you can pick anything, but I will come to that later. And third step, and that's again very similar to Neyman-Pearson approach, you find the critical value for that chosen test statistic such that under the null hypothesis in one, here, identical probability distributions, that the probability of exceeding this critical value is controlled, just like Neyman-Pearson. Now, this critical value is defined by some critical p-value under, now it's not the sampling distribution, it's under the permutation distribution. Yeah? Now, what are the differences with the Neyman-Pearson approach? I already briefly mentioned. First, the null hypothesis is now about the probability distribution of the observations, and not about the unknown population parameters. Second, that's very important, the p-value under the permutation distribution, you can calculate this for every test statistic without any auxiliary assumption. So there's no normality whatsoever. And there is also the opportunity to go for a particular test statistic that is chosen specifically for the type of effect that you hope to encounter. And that's actually mentioned in point 3. If you want your test to be sensitive for a particular aspect of your data, and I assume you are well informed about the neurobiological mechanism that you are hunting for. If you know a particular pattern in your data, that's what I want to detect. Then, prior to collecting your data, you can come up with some test statistic that, on the basis of a priori arguments, is likely to be very sensitive for that pattern. If you look for a particular type of coherence between right temporal and left frontal areas, then you more or less know how you have to devise a particular test statistic. You can make your test statistic such that it's optimally sensitive for your favorite phenomenon. And the permutation distribution will give you a valid p-value to test this null hypothesis, equal probability distributions, with optimized sensitivity for your type of effect. Okay, this is the rationale, the formal rationale behind permutation test, and it looks very much, the schematic looks very similar to the Neyman-Pearson approach. There's only a few differences. There is a difference here. This is where the null hypothesis is. And there is a difference here. This is the way that you arrive at your reference distribution. So I'm going to start here. So here, that's the null hypothesis that you test. And the null hypothesis pertains to equality of the probability distributions in the two conditions that you are comparing. And I've written down a conditional distribution here. I'm going to say a little bit about it. It is so this small part in my slide. It's a little bit of mathematical beauty in the permutation-based approach. I'm going to try to give you a gist of it, but if you want to know more about it, you should go a little bit into the literature. So what is being depicted here? It's a conditional probability distribution. And what you see behind this vertical line, that is behind the vertical line, it is the event on which you condition. So it's a conditional distribution of my data given the unordered observations. So this D is one vector in a between unit of observation designs 2 times n numbers. And what is behind the vertical bar, it's the same numbers but then unordered. The same numbers, but ignoring their order, which involves that the observations in condition A could just have well been at the locations where the observations for condition B had to be. Now, crucially, what you can prove in a very short but very elegant proof is that if the random variables in condition A and those in condition B, if they have the same probability distribution, then this particular conditional distribution, the ordered data given the unordered data, that's a uniform probability distribution. So under that hypothesis, the null hypothesis we want to test, it holds that this conditional distribution, the ordered data given the unordered data, is uniform. It means that each of the ordered data given the unordered data is equally likely. And drawing from a uniform distribution is very, very easy. It's trivial. You can write this in one line of code. Every ordering of the 2n data points is equally likely. So we can just use pseudo-random number generation to create different random orderings with all with equal probability. Each of these random reorderings with equal probability, we can feed them into our favorite test statistic, construct a histogram, that's our reference distribution. Under this null hypothesis, we have our observed data we look how far it is in the tail, extract the p-value, and make a decision. Perfectly valid to evaluate this null hypothesis. Very quickly, for a within unit of observation design, it just works the same, except that now the permutation is not achieved by swapping the condition A and the condition B unit of observations without respecting any structure. Here, in a within unit of observation design, we have this structure that every subject is being observed in two conditions, and we have to respect that structure in our permutation procedure, and this involves that we only permute the elements within every subject. So for subject 1, we can permute those two. For subject 2, we can permute those two, but it's not allowed to permute those two. You cannot replace a data point of subject 1 by a data point of subject 2. But for the rest, the logic is just the same. Okay, now how works this in practice? Yeah? And what I'm going to show you now is a particular test statistic. I call it a homemade test statistics, which I would all advise you to do, to make homemade test statistics in a way to improve your sensitivity. And the homemade test statistic that I have built here, it's also built into Field Trip. It's based on clustering. It's based on clustering adjacent time points. Yeah? And that makes a lot of sense from a neurobiological perspective. Yeah? If you have, so in a time-locked trial, if you have observed an effect, say at 302 milliseconds post-stimulus onset, and there is an effect there, most likely it will also be there at 303, 304, 305. So you should not consider these samples separately. You should combine the evidence against the null hypothesis across those adjacent samples. The same holds for space. If you observe an effect over P3, most likely PZ will also give some evidence against that null hypothesis. So it really makes sense to cluster the evidence across time, across space, and across frequency. And here is a simple example where we only cluster across time. And it's also the data that you are going to analyze. You can actually reproduce exactly this figure here. This is the we call it the Nienke-Weber study. It's one of the first magnetic N400 studies that we have conducted here. I have taken one channel here. It's a left temporal channel. Left temporal channel. There are two experimental conditions. This one is semantically congruent, and the other one is semantic incongruent. So you all know the N400 phenomenon, I think. Yeah? Should I explain something about? No? Okay, I'll not do this. Okay, there's two experimental conditions, and what we observe is that in the semantically incongruent condition, you see a nice evoked response which starts around 300 milliseconds, which has died around 800 milliseconds. Yeah. So the experimental effect that we're talking about is the difference between the solid line and the dotted line. Now, how can we go about to quantify the evidence against the null hypothesis for this difference? So what we do in the first step, we calculate t-statistics. We calculate t-statistics for each of the time points. And I think we have a sampling rate of 600 Hertz, so we have 1200 points here, 1200 t-statistics. And the naive way to go about here is just to calculate a t-statistic for each of the time points. And then you see, hey, they are significant here for from 400 until 600, or from 4 until 700. But that's significance for each of the individual samples. And you may imagine that if that peak is a little bit less high, then you may start doubting, hey, is this as a whole, does that exceed the critical value enough to reject the null hypothesis, yes or no? And this shows you the multiple comparison problem that you get into. So now how does the cluster-based permutation deal with this? The cluster-based permutation makes use of the t-statistic as a thresholding device. Yeah? It does not use the t-statistic to calculate the p-value, but it uses the t-statistic as a kind of a standardized effect measure, and it chooses a particular criterion value, a threshold value to identify time points that have evidence against the null hypothesis. And so you see we thresholded here at 1.96. You could have taken any number. You could take 2 or 2.5. It doesn't really matter for the statistical properties of the eventual test, of the permutation test. It's just you need some threshold to identify time windows where there is evidence against the null hypothesis. And all these time windows, I have depicted them here. These are all the time windows where this t-statistic exceeds in either direction the critical value. Now I have these time windows, and I'm now going to combine the evidence across all these time windows in one number. And the way I'm going to do this is by making use of the assumption that evidence against the null hypothesis occurs on adjacent time points. So what I will do is I will look for contiguous time windows, and I will take the time window that is the longest, and it turns out to be this one. There's also one here, one here, one here, one here, but they're very small. But this guy is very big, and I calculate the area under the t-curve here. And I take the maximum area under the t-curve. And that's going to be my final test statistic. So with this number, the area under the t-curve, under the thresholded t-curve, that is going to be my favorite test statistic. I like it because it takes into account that any genuine evidence against a null hypothesis should be contiguous over time. And the same thing holds for space and frequency. So now, how do we arrive at the reference distribution to evaluate whether that observed area under the curve is large enough to be sufficient evidence against our null hypothesis? And that's something that we achieve by randomly permuting the congruent and the incongruent trials. It goes as follows. If you randomly now permute congruent and incongruent trials, and if you would then look at the difference between the dotted and the dashed line, they would only be random differences. Because if you randomly permute congruent and incongruent, you're just destroying the effect. So after random permutation, the solid line, which does now not consist of genuine congruent trials, it's just half congruent, half incongruent, and the same holds for the dotted line. Both of them, they would be about, have more or less the same trajectory. And because they have more or less the same trajectory, the corresponding t-statistics, that would be centered at 0, and there would be approximately 5% of the samples would exceed plus 1.96 and or minus 1.96. So after random permutation, you would see this t-statistic time course to wiggle a bit like this. Now, if you have this wiggly t-statistic time course without any pronounced peaks and troughs, we use that wiggly t-statistic time course to calculate exactly the same test statistic that we also calculated for our observed data. So we're also going to threshold at 1.96 and minus 1.96, identify contiguous time intervals, calculate the maximum area under the curve, and that maximum area under the curve, that will then go into our reference distribution for our test statistic. We do this a very large number of times, get an histogram, calculate the p-value using the observed statistic here. That's how it works. And here, summed up the procedure. So it works it involves 6 steps. First step is you calculate a t-statistic for each of the samples in the multidimensional data structure, and we have considered this case only temporal data, time samples, but you can do it just as well using spatiotemporal data or spatio-spectrotemporal data. You threshold these sample-specific statistics, you construct connected clusters of these samples across time, time-space, time-frequency space, clusters that exceed the threshold that all have the same sign. We do this separately for positive and for negative clusters. Then you calculate the cluster level statistic by taking the sum of the sample-specific t-statistics, you take the maximum of these cluster level statistics, and you evaluate this maximum under its permutation distribution. That's all. This is an example of how you do this with spatiotemporal data. It's just the same story, except that now you also have a spatial dimension, and the clusters that you get are not only temporal clusters, but as a result of the low SNR of most biological signals, and also the high dimensionality of its data structures. I believe that neuroscience cannot do without statistics, despite the fact that it will not allow you to reveal the truth. You have to do something with the uncertainty in your data. Third, every decision-making principle that you use in neuroscience must be able to solve the multiple comparison problem. Fourth, I believe that permutation tests are ideally suited for neuroscience for two reasons. They allow you to solve the multiple comparison problem without making auxiliary assumptions. And second, they can increase sensitivity by incorporating biophysically plausible constraints in the test statistics. And I have done some simulation studies, and if you go to spatiotemporal data, the advantage of permutation-based methods, especially in combination with clustering, it's spectacular. You can just try out for yourself by running a small simulation study. This is work that I have done with colleagues where we describe the methods and some references of applications, actually quite old. Yeah, it turned out to be an extremely popular method nowadays. I think it's cited almost once every day. I'm very happy about this. About 8 years ago, we started with this, and then I advertised it here in exactly this course, and we had 2 citations in the first year. And so you see, by teaching in a field trip course, it really helps in getting cited. So that's all. So enough jokes. Questions? Anke Marit.
So I was wondering, in this example that you give,
Which one?
yeah, this one.
Yeah.
So you have an exceedance at several time points.
Yeah.
If you permute, you might get also critical exceedance at different time points.
Yes, yes, yeah.
So how would you go about in this case? Would you either have to restrict it to specific time points, or would you just in this case interpret it as somewhere in this period?
Yeah, your question, it's a very good question. I always get this question, and I also, in the psychophysiology paper that I refer to, I also spend a few paragraphs on that issue. Oh, thank you very much, thank you very much. So Anke Marit asked the following. Different from this example here, where there is very clear a deviation from what you expect under the null hypothesis at one particular time interval. It might also be, and I have also observed, that in the same experimental contrast, it is not just one time interval that turns out to be to exhibit such a strong difference against the null hypothesis, but multiple exhibit a strong difference. And you also have this over space. In some experimental contrast, you have a left frontal effect and a right sensory motor effect. Statistics doesn't have a good answer to that. What statistics can do very well is making decisions about null hypotheses. And now remember the null hypothesis that we are testing here. That null hypothesis is a very global null hypothesis. And in this case, if we look here at this one time series, at one channel, cortex. But now assume you have you're running experiments with professional subjects, you don't have to pay them, and you run not a session of 1 hour, but you have them return every day. And you have collected hundreds of thousands of trials from them, from a series of 30 consecutive days. And then you do this where all of the people in his lab had to be a subject every 2 days, and that for a couple of months. And then in very simple sensory motor tasks, also the bold response. And it's something like, instead of moving your index finger, you were moving your pinky. At some point you could also find significant differences in the frontal cortex. So this just occurs. But the uncertainty in that spatio-temporospectral localization of the effect, that uncertainty cannot be quantified by a p-value or by a confidence interval. So, and it's a very long story, Ankumara, because I also try to answer the ideas behind it. And I was a bit prepared because I just get the question every year. It's a very legitimate question. And the bottom line is, don't use statistics for everything. Use statistics for rejecting a null hypothesis, but then for characterizing the spatio-temporospectral structure of your effect, use other methods like source reconstruction, for instance, and clever experimental manipulations.
Would it be different if you a priori specify, like you can...
Not all, though. But those interaction effects that are most common in neuroscience can be tested. And that is because most of these interaction effects, they pertain to within unit of observation designs. So now you typically have a factorial structure in your experiment. You not only have 2 experimental conditions, but you have 2 by 2 experimental conditions. Actually, you have 4 experimental conditions. And you want to know whether the effect of independent variable A is different according to the levels of independent variable B. And the way you actually do this in your calculation is that you calculate difference scores, mental variable B at each of the levels of variable A. So you have 2 difference scores. And if you now want to compare the average of these 2 difference scores, it's just again a paired samples t-test. But it's now a paired samples t-test using difference scores and not using within single condition observations. And the whole logic applies. When doesn't it apply? It doesn't work if you want to test interactions in between unit of observation designs. So if you have an experiment, say you have male and female, and you have young and old aspects. So actually, it's a bit more complicated than what I tell you now, but this is the gist of the idea.
And if you would have 2 groups and 2 conditions, could you then use it? So if you want to know whether 2 groups differ in 2 conditions and different...
Yeah, on the difference, sure. Then you have an independent samples t-test again at the level of the difference scores. So you calculate the difference score for every subject. Then you say you're still controlling your type 1 error rate. But this is with 3 test statistics that you have come up with a priori without looking at your data. Things become different if you have 1, you test at 0.05, it's not significant, and then you start eyeballing your data. And you think, I think the pattern looks a bit like this. Let's see if I can find the test statistic analysis. Your analysis is not just one p-value. There's a whole series of analysis, and you try to build a consistent story, and that also is useful for convincing reviewers. Don't try to shoot a reviewer a small p-value in his eye, especially not a fabricated p-value. Don't do this. Questions?